Please grab your notebook and a paper. In this video, I'm going to be reviewing current and resistance. Along the way, I'm going to ask you to pause the video and answer questions. I know you don't want to actually do that. You don't even probably want to watch this video, but this will be a good way for you to check and make sure you really have an understanding of these big ideas that you should have learned over the last few activities. So grab a pencil, grab a paper, and get ready to write down some answers. So first question, define current. Go ahead and pause the video and answer that question. All right, hopefully you came up with the idea that current is the flow of electrical charge past a point. So we've seen this in the little models that we've done as we've created closed circuits. We've been able to see the flow of current or charged particles moving. This lab activity does a really good job of showing you the movement of electrons. Remember, current is the net flow of charge that's moving. So it's the total, the sum of the charge that's moving. And we have two different ways that we've shown it. The standard way of showing it in the PhET labs, like this one, is to show the electrons moving. But the way we actually usually depict current is using what's called conventional flow. And conventional flow, you'll see, is reversed from what actually happens as far as the actual electrons moving. The reason that this is conventional, as we learned before, is simply because we didn't know what was actually happening early on. And so we just picked a way and said that current always moves from the positive side of the battery, which is the side that has the little button end poking out, or the orange side in these batteries on the lab, towards the negative side of the battery. That again is conventional flow. So when you answer questions, you should really be answering questions in terms of conventional flow, which always says from positive side of the battery to the negative side of the battery. So next question, again, get ready to write down, pause the video. The question is, how can we identify the amount of current in a particular circuit? What are some ways we can identify the amount of current in a particular circuit? Pause the video, see if you can come up with as many different ways as you can think of to identify the amount of current traveling in a circuit. Go ahead and pause now and answer that question. Okay, hopefully you came up with 2 or maybe even 3 different ways to recognize the amount of current that is in a particular circuit. So one way that we cannot do with this online lab, because it doesn't have this built into it, but we did see earlier in a video that I created for you, is to look at the deflection of a compass. The more a compass deflects when it's put underneath a wire with current, the more current is traveling through that wire. So a big deflection means lots of current going through the wire. A small deflection means only a little bit of current is going through the wire. There are some ways we can look at the differences in current from this PhET lab. One that hopefully you can easily recognize is just the speed of the current flow, as shown by the arrows or by the electrons. So either way, as you look at those electrons, you can see a difference in the amount of current, right? The faster the electrons are moving, that's representative of a stronger or bigger current. And then the third way that we've been able to identify current in our circuits is by looking at bulb brightness. The brighter the bulb is shining, so the more width and length to the arrows that are representing the brightness, the more current is flowing through that bulb. So keep those things in mind as you work through the example problems today. Next question. What are some different ways that we can change the amount of current in a circuit? Go ahead and pause the video and see if you can come up with several ways to change the amount of current in a circuit. All right, let's check your understanding. Did you come up with the idea that you can change the number of batteries in the circuit? That is a big way to change the amount of current. Remember, batteries do not supply the electrons. There are already electrons everywhere in here, so they do not supply the charged particles. They just get the charged particles moving. So as soon as I close this circuit that has 3 batteries in it, you can see that we have much more current in this system than we do in this system with just 1 battery. So they both have batteries, wires, and a bulb. The only difference is 1 battery versus 3 batteries, and you can see that 3 batteries is getting the electrons moving much more quickly in this circuit than they are in this circuit. You can also see that the bulb is much, much brighter, another indication that there is more current in this circuit that has 3 batteries. If we had a compass, the compass would deflect much more in this circuit than it would in this circuit. A second way to change the amount of current in a circuit is to change the resistance in the circuit. So here I have a circuit that has a light bulb in it, and that light bulb acts as a resistor. You can get a sense of the fact that this is going to resist flow because of the thickness of the wire itself. So here we have a fairly thick wire, and here we have a much thinner wire, which is going to resist flow. We can check that by looking at the current when we have a light bulb compared to the current over here when we don't have a light bulb. Look what happens in this circuit when I just have wires with no resistor in it. Look at how quickly that current is flowing. This seems to have stopped because this had to speed up so much that this is actually playing only 1% of the normal actual speed this would happen. You can also see that when we do this kind of thing, we can get current to flow so quickly that it creates lots and lots of heat energy in something like our battery. You may have experienced this before with your cell phone. If you've ever been using your cell phone to do a lot of things simultaneously and been using a lot of current, maybe the screen's on and the speakers are on and the radio signal that's transmitting to the cell tower is on, and GPS is on. If all of those things are on at the same time, you can generate a lot of current in the battery in your cell phone, and your battery can get hot, or your cell phone can get hot because of that. All right, so another way that we can look at the idea of resistance and how resistance influences current is by adding additional resistance. So here we have 2 bulbs instead of just 1. What do you think is going to happen when I close the circuit? What's going to be true of the speed of the electrons? What's going to be true of the brightness of the bulbs? Go ahead and make a prediction in your notebook. All right, check it out. Did you predict that the electrons would be moving more slowly and that the bulbs would be less bright? Hopefully you did, because adding resistance is going to make it less likely for current to flow. So this brings up another question. What is resistance? Go ahead, pause for a minute and see if you can come up with a definition for resistance. Okay, check your answer. Hopefully you said that resistance is the opposition to flow of charge. So resistance is just anything that keeps charge from being able to flow through a circuit. The opposite of resistance is called conductivity. So the extremes in resistance are things that are conductors, allowing electricity to flow well, versus insulators, which don't allow electricity to flow at all, right? They're completely resistant to the flow of electrons. So one idea to think about is how does the resistance in a circuit or a pathway influence the path that the electrons are going to take? So here we have our normal, I'm going to go ahead and stop this one. Here we have our normal one bulb, one battery connected with wires. What's going to happen if I add another wire in here, and that wire, notice, is connected to the bottom of the bulb, and I'm going to connect the other side of that wire over here to the battery? Make a prediction. What do you think is going to happen, and why? All right, let's check your understanding. If I connect that battery to the wire here, notice the bulb, this really shouldn't be lit anymore. There's a glitch in here, but this bulb should now be dim. It shouldn't be lit up anymore. But we can definitely see that there are no electrons flowing through the bulb. I'm gonna cut right there and then reattach this that way and see what happens. So there's a little bit of a glitch in this program. This battery should not currently be lighting up this bulb, and we can see that like I said earlier, the electrons are no longer flowing through that pathway that has more resistance. The electrons always want to take the path of least resistance, so they're doing that through this big wire rather than trying to squeeze through that little wire that has much higher resistance. One way to think about resistance one way to show current and what's happening with current is by representing arrow tails. So we haven't done this yet, but we can use arrows and different numbers of tails to show the amount of current. This is like if we're drawing a circuit, right? So if we don't have an animation that can show current flowing, then we can show current through a drawing, and we can use arrows to show that. Notice it's not the length of the tail, it's the number of tails. So the more tails we have, the more current we're showing going through that wire. We also know that we can show the amount of current by showing the brightness of a light bulb. So here we have a bunch of different light bulbs, and we're showing different brightnesses. This would be dim because it has only a few light rays coming out versus very, very bright with lots of light rays. One last thing to think about is a little bit of an analogy for resistance. So one way that I can remember what resistance is by thinking about resistance as being similar to a straw. So imagine if you have to put one of these straws in your mouth, and then you're going to breathe only through the straw as you run all the way down the hallway or around the block. Which straw would it be easier to breathe out of if you had to use only the straw to breathe while you're running? Hopefully you can see that it'd be much easier to breathe through a thicker straw. There's less resistance in a thicker straw compared to a narrower straw. So straws maybe can give you a simplified way of thinking about resistance if you can use that as an analogy. All right, please stop in if you have any questions. Thanks so much.